let us discuss series. So what is a series? We remember from calculus, a series is just an infinite sum of the terms of a sequence. So it's like writing A1 plus A2 plus A3 and so on, okay? But it's an infinite sum, so we cannot really enumerate all the terms in the series. And this actually, the way the series is defined is as the limit of the partial sums, okay? I wrote here an, but I meant ak. So it's the limit as n tends to infinity of the sum from 1 to n of the ak. Okay, here the sum from 1 to n is a finite sum. It's like writing a1 plus a2 plus a3 and so on all the way to an. So we are going to be computing the partial sums and then taking the limit of those, limit of partial sums. Okay. Well, of course, some easy examples is the sum from k equal 1 to infinity of 1 over k, or the sum from k equal 1 to infinity of 1 over 2k, the sum of negative 1 to the k, and so on. Some of these will amount to a number, some of these will not converge, some of these will just go to infinity or negative infinity, okay? So we need to figure out the equation of convergence. And here, there is a meta theorem that says that every theorem about sequences can be restated as a theorem about series and vice versa, okay? Why is that? Because whenever we have a partial sum that we will call Sn, okay? Whenever we have partial sums, what we can do is to write each of the an from the sequence. Okay, we are going to, let me write this carefully. So we have a sequence a1, a2, and so on, and we have a series that is the limit of the partial sums, s1, s2, s3, and so on. Okay. The way the partial sums are defined, clearly s1 coincides with a1, and after that, we can always write an as Sn minus Sn minus 1. Okay, this is for n bigger than 1. This is clear, right? So if we write it in expanded form, it's going to be completely clear. So this is a1 plus a2 all the way to an minus 1 plus an minus a1 plus a2 all the way to an minus 1. Okay, so there is a cancellation here of these terms, right? And the only one that survives is an. And then we can also, this allows to write each of the terms of the sequence an in terms of series and vice versa. Okay, we can use these equations to move from one to the other. What does this mean? This means that every theorem that we learned for sequences, we can apply it to series too. For example, the Cauchy criterion, okay? This one says, it's basically the same Cauchy convergence that we saw for series. We have that a series converges if and only if for every epsilon bigger than 0, there is some integer capital N such that the sum from k equal n to m of the ak is less than epsilon for every m bigger or equal than n bigger or equal than capital N. Okay, and here's we see the connection. What we are saying with this condition is that the Sm minus Sn is less than epsilon. Okay, well, actually, this is not quite correct. What we are actually saying is Sm minus Sn minus 1 less than epsilon for every m bigger or equal than n bigger or equal than capital N. Okay, this is the Cauchy condition that we saw, that the terms would be closer and closer as n would grow. Okay. But here writing Sn minus 1 doesn't matter. Okay, one term more or less is not going to change the convergence of the series or the sequence. All right, so here there is one consequence that is interesting. So in particular, we can take m equal n, okay, and this sum from n to m, because we are only taking one term, becomes an lesser or equal than epsilon for n bigger or equal than n. Okay, what does this mean? This is the divergence test, which is the basic. This is useful to rule out silly cases, series that have no chance to converge. Okay, other than that is not very useful. But this one says that if San converges, then the limit of the an as n tends to infinity equals 0. Okay, for example, if we have the sum of the arctangent of n as n goes from 0 to infinity, let's say, okay, and we want to know if this converges or diverges, something that we can check is, okay, an is the arctangent of n, right? And the limit as n tends to infinity of the arctangent, remember the arctangent, the graph is like this. It has asymptotes, horizontal asymptotes at pi over 2 and negative pi over 2. So as we go to infinity, the arctangent, the limit is going to be pi over 2, which is clearly different from 0. And our theorem here says, when we turn around the implication, says that if the limit is not 0, then the zeros cannot converge. Okay, so the sum, the series with the arctangent cannot converge. Okay, so this is typical. It's like the first thing we need to check always is the divergence test. Okay, it's not going to be very useful because, for example, I mean, most of the time it's not going to be very useful, but it allows to rule out silly cases. For example, if I have the sum from n equal 1 to infinity of 1 over n of 1 over n squared, okay? Converse or diverge, and we want to know if they converge or not. The divergence test is not useful because in both cases, the limit is 0, but it's not saying anything, okay? When the limit is 0, then we don't know if it converges or diverges. Okay, this 1 over n is what I wrote an, and 1 over n squared is bn. Okay, so the sum of 1 over n diverges. This is calc 2, but we will go over this carefully later. And the sum of bn converges. Okay, so if the limit of an is actually 0, the test is inconclusive. Okay, this means we cannot conclude anything from this test. All right. Now, by the way, I wanted to mention, so this series here with the 1 over n, this is called the harmonic series. Okay, although I'm sure we all know that, but whenever I talk about the harmonic series, I mean the sum of 1 over n. Now, there is one type of sequences that we saw, right? The monotonic sequences. Okay. Here we had a theorem that says that bounded and monotonic or monotone gives convergence, right? We saw this in a previous video. And we can apply this also to series. Okay. We have this theorem. If we have a series, it can go from 1 to infinity or 0 to infinity, it doesn't matter. Okay, and we have that all the an are non-negative, so bigger or equal than 0. Okay, this one converges, so it's right here with. Okay, so this series converges if and only if the partial sums Sn, let me write the sum from k 1 to infinity, Sn from 1 to n of an, the partial sums form a bounded sequence. Okay, here the important remark, there is not much to prove actually. The important remark is that because all the terms A1, A2, and so on, they are all non-negative, right? Whenever I add one more, it's always going to be to give something larger. So it's monotonically increasing. So we will have that Sn is bigger or equal than Sn minus 1. Okay, and we have it from here, just writing it down. If I take out the an, I'm going to get something that is less or equal than the original. Okay, so this is monotone increasing. Okay, but then because we are saying that it's bounded, then it will converge. Okay. plus bounded implies Sn as a sequence converges. Okay. Why is this useful? It's actually useful because it allows us to use what is called the comparison test. This is the main tool to prove convergence or divergence. Comparison test. Okay, the comparison test says that if we have some an that in absolute value are less or equal than Cn for n large enough, okay, from some n0 onwards, n0 fixed, okay, and the sum of the Cn converges, then the sum of the an also converges. In this case, the an goes without absolute value. Okay, so here we are saying that if the larger one, okay, the sum of the Cn is going to be larger than the sum of the an, if the larger one converges, it will not allow the other one to go to infinity or negative infinity. Okay, it's keeping it in place, let's say. And then the second part, this applies only to non-negative sequences. If we have an bigger or equal than dn bigger or equal than 0, okay, this means non-negative. For n bigger or equal n0, and the sum of the dn diverges, the series, what happens then? Then the series with the an also diverges. Let me write it in the next line. Also diverges. Okay, so here what is happening is that the sum of the an is above the sum of the dn. So if the sum of the dn pushes to infinity, then it will carry the sum of the an along, okay? So this is our comparison test. And the way we use it is just comparing with series that we know that they converge or they diverge, okay? For instance, well, let me give the proof first. So for the proof, the first part A, this one is easy. We are assuming that the sum of the Cn converges. Okay, that means by definition that given epsilon, okay, there exists some n large enough, bigger or equal than n0, such that m bigger or equal than n bigger or equal than n implies the sum from n to m of the ck less or equal than epsilon. Here we have applied the Cauchy criterion. Okay, but now it's very easy because this is saying that if there is convergence, then the differences between Sm and Sn are going to be very small. Okay, again, as I said before, I should write here n-1, but it doesn't really make a difference. But when this happens, we can look at the same differences for the AK, taking absolute values just to make sure, because this is positive, okay? And applying the triangular inequality, we can bring the absolute value inside, okay? This means an plus 1 all the way to am, right? This we did in one of the exercises, just by induction, okay? And then here, by hypothesis, each of these is less or equal than ck. So the whole thing is less or equal than the sum from n to m of the ck, which we just saw is less than epsilon. Okay, so because epsilon is very small, this sum in absolute value of the ak is smaller than epsilon. And then by Cauchy, the series of the AK converges. Okay. And we have part B also. Let me copy. So for part B, this one actually follows from part A, right? Because notice what happens. Because an is bigger or equal than dn, we have that the sum of the dn is lesser or equal than the sum of the an. Okay. And if we have that the larger one converges, then the smaller one must converge. But that's a contradiction. Okay, because we are assuming that the sum of the dn diverges. Let us complete with one example. So let's take the sum of square root of n divided by n squared plus 2, n equal 1 to infinity. Okay, and here what we are going to use is that the square root of n divided by n squared plus 2, this is less or equal because n squared plus 2 is bigger or equal than n squared. So this is less or equal than the square root of n divided by n squared. And that makes 1 over n to the 3/2. Okay, so this is less or equal than the sum from n equal 1 to infinity of 1 over n to the 3/2. And this one is convergent. Okay, we will see that in a video, that whenever we have 1 over n to the power p, n equal 1 to infinity, there are two cases. Okay, let me write it carefully here. This we call p-series test, okay? So what we will see is that this converges if p is bigger than 1 and diverges if p less or equal than 1, okay?